Okay, horizontal stretches, compressions, and reflections of radical functions. So now we're going to look at the effect of multiplying the x by a value of k inside our function. And what effect this has when we're talking about the radical or the square root functions is that it's going to look like this. Y equals the square root of kx. And now the k is this constant value that's inside the function. So we're going to say that's inside the function. And what that does to the function is that it affects the x values. Okay? Why? Because everything inside the function affects your input. Everything outside the function affects your output. So whatever affects your input will affect your x values. So let's look at the effect of what happens when we adjust the k value. So k is greater than 1. So here on Desmos, here I have the base function. Right now k equals 1. So here we have the graph of y equals the square root of x. Now I want you to look at the point on this graph right here at 4 and 2. Okay, I want you to look at what happens to that point in relation to the origin, because the origin is always going to be 0, 0 right now. But when I adjust the k value, have a look at what's happening to that green point. So I press play. You can see k is increasing. Now what's happening to the green point? It's getting closer and closer to the origin. It's getting compressed. It's getting compressed horizontally. Okay. So here, if I pause it for a second, let's move it. So here, k is 5.2. That means this point right here, it went from 4 comma 2 to 0.769 comma 2. So the x value got divided by 5.2, roughly about 5. Okay, so it is a horizontal compression. So this graph compressed horizontally. It may look like a vertical stretch because you can see the square root function as k goes up. You can see it looks like it's a vertical stretch. But when we're talking about the inputs only, we're going to talk about things in terms of x, in terms of the horizontal. So we say this is a horizontal or horizontally compressed by, well, if we're dividing by, let's say 5, it's going to be 1 over 5 or 1 over k. Horizontally compressed by 1 over k. Okay? That means you're multiplying all your x values by by 1 over k. Okay, now what happens when you're talking about k values between 0 and 1? So let's change our parameters here. I'm going to now change this k, so from 0 from the left end to the 1 on the right end. Let's make the steps even smaller. Okay, so let's have a look. So now you can see the green point getting further and further away. It's getting stretched. This is a horizontal stretch. Horizontal stretch. I'm going to pause it right there. Okay, let's actually bring this back a little bit there. So here k is 0.4. Well, what happened to the coordinate? The x got bigger. Okay. So I'm gonna call this a horizontal stretch. Horizontally stretched by 1 over k. So again, think about that x value. If x was equal to 4 in the base graph, then you take that 4 times 1 over 0.4 and you get 10. That's the new x value. So it had to be 1 over k. Okay, so it's a horizontal stretch. So we're going to use this idea and we're going to create some graphs. So let's talk about the parent function, xy. Let's put the points 0, 1, 4, 9, and the y values are 0, 1, 2, and 3. And now we're going to map some other functions. Let's try k greater than 1. Let's try a k value of 2. So k equals 2. So you pick a value of k. So what happens? We're going to multiply our x values by 1 over k, so 1 over 2. So my x values become 0. 1 divided by 2 is 0.5. 4 divided by 2 is 2. And 9 divided by 2 is 4.5. Y values do not change, so y stays as 0, 1, 2, and 3. In the case of, let's say, k between 0 and 1, let's pick 0.5. Well, that means my x values, I'm going to multiply them by 1 over k, so 1 over 0.5 is equal to 2. Right, so 1 divided by 0.5 equals 2. Okay, so 2 times my x values from my parent function. So my parent function 0 becomes still 0. 1 times 2 is 2. 4 times 2 is 8. And 9 times 2 is 18. My y values still remain the same as the parent function y value, 0, 1, 2, and 3. And now I can graph these three functions. So here's the base function. Y equals the square root of x. Here's the one that is horizontally compressed. I'll do that one in a different color. So 0, 0, 0.5 and 1, 2 and 2, 4.5 and 3. So here is my horizontally compressed graph, y equals square root of 2x. And let's do the third one, here the horizontally stretched. So 0, 0, 2, 1, 8 and 2. I can't plot 18 and 3, so that's good enough. And here's my horizontally stretched graph. Y equals the square root of 0.5x. Okay, let's look at horizontal reflections now. What happens when I put a negative inside my function? Again, because it's in the inputs, you're going to affect your x values. Negative x. Well, when the negative was outside the function, we had vertical reflections along the x-axis. Now, if the negative is inside the function, you're going to have reflections along the y-axis. Okay, so if the negative was outside, so here again, negative was outside, you had a reflection on the x-axis or the horizontal axis. Now, if you put the negative sign on the inside, you have a reflection along the y-axis, the vertical axis. Okay, so that's a graph reflected in the y-axis. Okay, so let's just sketch the graph on our grid. So parent function 0, 1, 4, 9, 0, 1, 2, and 3. The mapping would look like this. You multiply your x values by -1. Okay, so 0, -1, -4, -9, but the y values still remain the same as the parent function. In mapping notations, looks like -x, y. And graphing it would look something like this. It's just the square root function reflected along the y-axis. Okay, what if we threw in another transformation? Square root function reflected in the y-axis and translated right 1 unit. So again, writing the parent function down. Now, for reflection in the y-axis, I need to multiply my x value by -1. And for translation to the right, you have to add 1. Okay, so +1. So reflections come before translations. Multiplication comes before addition or subtraction. So it's -x plus 1. Take your x values 0, 1, 4, 9, and multiply them by -1. So 0 times negative is 0, plus 1 is 1. 1 becomes -1 plus 1 is 0. 4 becomes -4 plus 1, which is -3. And you have -9 plus 1, which is -8. Y values still remain 0, 1, 2, and 3. Plotting my points, 1 and 0, 0 and 1, -3 and 2, and -8 and +3. Connecting my points to make my curve, I get my square root function reflected along the y-axis, and also shifted to the right by 1 unit. In mapping notation, this would look like this, -x plus 1, y. Okay. Now note, whenever you have a negative in front of your inside your input, that negative k value, you should be, and you can write it out. That's how we wrote it out in mapping notation. Like that's what you see here. But if you were to write out the equation, you always must factor out the negative and put everything else in brackets. Okay. So if I were to write this example as the function equation, it would be y equals, or you could say f of x equals the square root of negative has to be factored out. So instead of saying x plus 1, you're going to say x minus 1, right? Because if you multiply -x times -1, negative of -1, which becomes +1, okay? But this shows, this writing the equation this way shows that I have a horizontal translation to the right by 1 unit. Remember, think about that opposite signs, x minus 1. It actually means to the right. Okay, and my k is now factored out as a -1. Okay, let's look at a couple of examples. Here is y equals the square root of 1 over 3x. The base function, again, square root of x. What's the transformation? Transformations are 1 over 3. So k is equal to 1 over 3. That means we have, if k value is between 0 and 1, we have what? Well, we have a horizontal stretch. By what? By a factor of 1 over k. So if k is 1 over 3, then what we're talking about here, let's write it down here actually. So 1 over k equals 1 over 3. Okay, so remember k is equal to 1 over 3. But the actual horizontal stretch is a factor of 1 over k. So 1 over 3 is just equal to 1 divided by 1 over 3, which is equal to 1 times the reciprocal 3 over 1, which is just 3. So by my mapping notation, I'm going to write 3 times x. Okay, and we keep the y value the same as it is. All right, so 3 times x. If I just draw the points really quick, so for x and the square root of x, we have 0, 1, 4, 9, 0, 1, 2, and 3. And then we have 3 times x, and the y values don't change, so it's 0, 1, 2, and 3. But 3 times x is 0, 3, 12, and 27. Now, I can't plot 27, but I can plot the other 2 points. So 0, 0, 3, and 1. Well, 12 and 2 would be somewhere out here anyways, right there. So it's going to be really stretched, horizontally stretched. Okay. Now, what about this example? Negative of the square root of 1 over 2x. So here we have k equals 1 over 2. And we have an a value of negative 1. So now we have a vertical reflection on the x-axis. So that's going to affect my y values. The k value is going to affect my inputs, the x values. So if k is 1 over 2, we have, again, another horizontal stretch by a factor of 1 over k. So a horizontal stretch by a factor of 1 over k. Why? Because k is a value between 0 and 1. So what's this 1 over k? Well, 1 over k is equal to 1 divided by k, which is 1 over 2, which is equal to 1 times the reciprocal, 2 over 1, and that's equal to 2. So this number here is going to be the mapping notation multiplication factor. So my x-coordinate will be multiplied by 2, so it's 2x. And the vertical reflection, the a value of being negative 1, means my y will be multiplied by negative 1. So if I looked at mapping my coordinates, x and y equals the square root of x. Here are my key points again on the parent function, 0, 1, 4, 9, 0, 1, 2, and 3. And now I'm going to map them. Here I have 2x and negative y. So 2x would result in 0, 2, 8, 18, and negative y will result in 0, negative 1, negative 2, and negative 3. Plotting these coordinates, I would have 0, 0, 2, negative 1. This way rather. Yeah. 8 and negative 2. And there's my graph. Just like that. Okay, so that was an overview of horizontal reflection, stretches, and compressions, and that ends this video.